Hello, everybody. Welcome to your Unit 2, Section 7 Chem Talk. Mr. Rafferty here. We're going to be talking about acids and bases. So make sure you have your green sheets out, open to page 33, Section 7. All right, so let's get started. You can click the continue button when you are ready. Some examples of acids and bases in everyday life. Car batteries use concentrated sulfuric acid to help the energy flow through your car to power all of the electronic systems. Right? Duracell batteries, they contain potassium hydroxide, or KOH, which is a base, right, allowing it to conduct electricity and power electronic devices. Right? Drano, if you ever have a clog, a very serious clog in your pipes, Drano uses concentrated sodium hydroxide, which can cause some chemical reactions, allowing your clogs to be released. Right? Nair, which is a thing that can make your hair dissolve right off your body, is an example of a base that is calcium hydroxide, while hair dyes use ammonia, which is another common base that we see around us. All right, so our notes will start right here with dangers of acids and bases. Most acids are dilute or weak enough to be fairly harmless. Most things you eat are pretty acidic, but they are not causing you to keel over and have to go to the hospital. So we eat acids. Some common ones are vinegar, which is in chemistry we call it acetic acid, or citrus fruits, which contain citric acid and vitamin C. Right? And in order for our bodies to digest the food that we eat, we have hydrochloric acid, which is a strong acid that will help break down your food. And we call these gastric juices. I'm not going to click on the hydrochloric acid and cheeseburger video. Just know it is just as disgusting as you could imagine. But if you wanted to, you can feel free to YouTube that on your own. If you find a guy with crazy Einstein-type hair, you know you are on the right path. All right, so some more dangers of acids and bases, and I apologize if any of these images are unsightly, but these are a real possibility if you are not working properly in the chemistry lab. All right, so concentrated hydrochloric acid or exposure to concentrated hydrochloric acid for just a minute or less, we can rinse it off and you'll probably be fine with no side effects. But, right, and again, I'm sorry for the images here, but if we don't wash it off, right, it can do some damage. Nitric acid attacks the protein, so exposure would turn your skin yellow and cause it to peel from damage. Sulfuric acid will severely burn your skin, right? You can see the damage from sulfuric acid at the bottom left here. And hydrofluoric acid, while it may be considered a weak acid, can be fatal if you just breathe in some of its vapors or spill a little bit on your skin. Okay, so the way we categorize acids as strong and weak has nothing to do with its danger to us. Okay, so make sure you are aware of that misconception, because hydrofluoric acid, while it might be one of the most deadly that we have, is considered a weak acid. Alrighty, so here's a look at our pH scale. As we get closer to 1 or 0, we're becoming more acidic. As we get closer to higher numbers like 13, 14, we get less acidic and more basic. And 7 will be neutral. So you can see pure water is here neutral. And over to the left here are some examples of acids. And to the right are examples of bases. All right, so we will use the pH scale to tell us right, how strong or weak certain acids and bases are. All right, so pH scale, this is a scale that tells us how acidic or basic something is. All right, let's see, where does this blank go for you guys? This blank is on the middle of page 34. If you want to fill that in before we go and start to fill in the different properties of acids, bases, and neutrals. All right, so we already went over our results for the lab. So some properties of acids. So acids turn blue litmus paper red. They react with metals. They feel normal or like water. Phenolphthalein remains clear. Universal indicator turns red or orange or pink, any of those warmer colors. It can be a weak or a strong conductor of electricity, but it should be able to conduct electricity. And its pH will range from 0 to 6. And so these are our properties of acids. I would definitely make sure you star this and that you know these. One way that I can help remember that blue litmus paper turns red for acids is that our end result of the litmus paper always matches up with our universal indicator color. So if you can remember that universal indicator turns those warmer colors like red and orange, then you should know that acids with litmus paper should be turning red. And our examples of acids would be Pepsi, vinegar, and lemon juice. That was not correct. Let's see. All right, and we go to properties of bases. All right, so right below, a lot of these are going to be just the opposite of the acid. So instead of what we had for acids, now red litmus paper will turn blue for bases. They do not react with metals, and they feel slippery or soapy. Right, that makes sense because soap was an example of a base for us. Phenolphthalein turns pink. Universal indicator turns dark green or blue. Bases will be either weak or strong conductors of electricity, but they should conduct. And we lost our spot again. Alrighty. And pH ranges from 8 to 14, and our examples would be Tums, window cleaner, and soap. Alright, so that should wrap up page 33. Let's wrap up page 34. So neutral solutions. Right, for neutral solutions, the litmus paper does not change color. They do not react with metals. Phenolphthalein will remain clear, just like with acids. So that can tell us that phenolphthalein is used to tell us if we have a base or not. So phenolphthalein is an indicator for basic solutions. Universal indicator will turn a light green or a pea green if we are neutral. It may or may not conduct electricity. We know from our lab that pure water did not conduct electricity, but when we dissolved salt in water, it did. When we dissolved sugar in water, it didn't. So we have some conflicting results there. pH of a neutral solution is always going to be 7. And some examples would be water, salt water, and sugar water. Alrighty, so that wraps up our properties of acids, bases, and neutrals. I would definitely start all 3 of those squares. These are properties that you are certainly going to need to know for the Section 7 quiz. All right. In class, your teacher, either myself, Mr. Arrow, Ms. Staub, should have done the glass rainbow tube demo, right, just to show how universal indicator can show a great range of colors based on the acidity or basidity of our solution. All right, and it should have looked like this, right? If I can take this bar out of here and kind of turn it upside down, it would look just like our rainbow tube. So this diagram, right, with colors can tell us what our pH is. So even though we don't have a direct reading that tells us, right, you can use your indicator, whether it's a paper or a droplet, to observe a color, and then you can predict what the pH of that solution would be. All right. Some other examples of indicators. If you're testing like for the presence of like methamphetamines or drugs, that is an indicator. It's looking for the presence of a certain molecule, and if that is there, then a color will show up, right? Pregnancy tests are testing for a certain hormone in a woman's urine, and if that hormone is present, right, another line will indicate that the woman is pregnant. If you have a fish tank at home, right, you can have the sticker on the side that the numbers will change color depending on the temperature inside your fish tank. This is usually temperatures in degrees Celsius. All right, drug tests we had already talked about. I think this is testing water. Some other examples might be like the spoons that we brought out in class that can change color when they get cold or warm or not. They used to be available at Sweet Frog. basically anything that will change color or appearance to indicate or tell us that something is present or something has changed. Okay, and phenolphthalein and universal indicator are not the only indicators we would use in chemistry class. There's a whole variety of them, and they can tell us a little bit more about the pH of our substances based on when they change color or which ones change color. Okay, so if we saw a substance that was yellow with methyl red, but red with methyl orange, then we know, right, it must be a strong acid and not a weak acid. So let's do some questions here. You can see we have our types of indicators listed here on the left. We have our pH down on the bottom. Right? So let's use this chart here to answer these questions. A substance that is blue when bromomethyl blue is placed in it is a base. So we want to look at bromomethyl blue. Right? If it's blue, that means it has a pH from 7 to 13. To say that is a base would be true. Okay. Number 2, phenolphthalein is placed in a substance and remains colorless. The substance must be an acid. So if I'm looking at phenolphthalein as colorless, right, it's not only just acids that would be colorless, but also neutrals as well. So that would be false. Okay. All right, so we can try another one. A weak base would be yellow with methyl red in it. Is that true or false? So if we're looking at methyl red and it's yellow, right, that does tell me that it would be a weak base. Now, actually, we kind of want to work backwards here. We know that, right, if it is a weak base, it would be yellow because from the ranges of like 7 to 9 pH, right, our low levels of basicity, we would be yellow. And the substance in the presence of indigo carmine must be a strong base if it's yellow. That would be true or false depending on how you want. Indigo carmine does indicate we have a strong base, but we could have a base with a pH of 11 that, if you wanted to argue was strong, could possibly be considered correct. Okay. So another review question here. You observe the following about a mystery substance. It has a slimy feel. It turns universal indicator blue, and it is a good conductor of electricity. What could you tell me about this substance? Would it be an acid? Would it be a base? Or would it be neutral? And then what would happen if we put phenolphthalein in that mystery solution? Would it turn pink or would it stay clear? All right. And then lastly, on the bottom of page 34, we have our common acids and base. All right, so we can recognize our acids because they typically all begin with the element hydrogen. Right? All of our examples here start with the element hydrogen, and we can recognize our bases because they typically end with a hydroxide or an oxygen bonded to a hydrogen, but it's not always like that. So our first 4 all have that as an example, but the sodium bicarbonate here, also known as baking soda, which would act as a base, does not have the hydroxide present. So it's not always the case, but that would be what I would use as my key to being able to identify a base. Alrighty. And then last thing we have here are neutralization reactions, or neutralizing acids and bases, and this is something that chemistry teachers do every year to dispose of that acid waste container. So the process of an acid and a base reacting to form a neutral substance is called neutralization. Right? And neutralization reactions will always occur similarly to a double replacement reaction. So your products will always be an ionic compound and water. So if we have an acid plus a base like we have here, our products will be an ionic compound, in this case sodium chloride, plus water, right? While this doesn't look like water, right, we have 2 H's and 1 O, right? So even though it's written HOH, that's still H2O or water, okay? So we should be able to have a little bit of practice here in your Chem to Go with these. Your product should always be an ionic compound plus water, right? Your water comes from your first hydrogen and then your hydroxide, and then your whatever's left will make your salt. Alrighty. See you later.